is going to be my starting velocity, v sub r, times my time step. So let me put this in here too, in units, right? So in other words, I know what my analog v sub r is, my continuous time velocity as a function of r. I multiply it by the time step I've chosen. That gives me an initial delta r0. Likewise, I can make it an initial delta theta sub 0 by saying this is v theta, the initial condition. Let's put a 0 there to denote the initial condition. And let's say for v theta, I've got to divide by r naught and then multiply by delta d in order to get my initial increment for angle. Once I do this, now I have a system of 4 pieces of information that I can start with. And all I have to do is keep updating these pieces of information. So for time increment number 1, I'm going to start from these, and then I need 4 equations that give me the next estimates for r1, theta 1, delta r1, and delta theta 1. And then for the next delta t increment in time, I need the same set of equations should relate my r1, theta 1, delta r1, and delta theta 1 to my r1, r2, theta 2, delta r0, and delta theta 2. So we're coming up with a set of difference equations to discretize this dynamic system. But here we already have the first set of equations. Let me go ahead and write the whole discrete system down so that you have it, and then we'll talk about it. So this is my algorithm. R at time sample n plus 1 is equal to r sub n, my previous sample, plus whatever my delta r n. So that makes a lot of sense, right? If this is my starting point, and I know what my r velocity is, I just multiply by delta t, that gives me my delta r sub n increment, and that's what I'm going to move to the next point as. Likewise, theta n plus 1 is going to be equal to theta n plus delta theta n. These are all 4 pieces of information that I can get from an initial condition. I just keep marching them and marching them. However, I also have to update these 2 pieces of state information based on the dynamic system, the discretized differential equation over there. What is this one? This is going to be delta r sub n. So my velocity, my r velocity increment is going to be equal to the same thing it was on the previous time sample, plus a discretized version of that the differential equation. And in some ways, looks nothing like the equation itself. It'll take a little bit of visual acrobatics to see where I got this. So okay, what's happening here? This delta r increment, essentially the r component of your velocity, is equal to the previous one plus this system here, which is really just a discretization of this up here. You kind of take that form. I got a delta theta, so then I'm squaring it, that's kind of like this over here. But I have this weird r plus 1/2 delta r sub n. And this is a little correction factor due to the fact that we're taking in order to get the second derivative with respect to time, we're taking the derivative of a derivative. And when you discretize a system like that, you're basically saying, okay, I'm looking at the difference between these 2 points and the difference between these 2 points. And I'm looking at that difference in here. And if that difference is going to be halfway between one difference and the other difference, so why you need this correction factor to get everything to work out right. And then finally, this last one is 2 delta r sub n, delta theta sub n, over r sub n plus 1/2 delta r sub n. And so here you have it. The demo is actually in the derivations, and I think I have an example problem online where you can actually just go through and derive this yourself and verify where the terms came from. It's a good exercise to work through. But once you codify the mathematics like this is a very trivial computer program to write. In fact, where are my aerospace guys? Right here. Okay. Whatever template you have to program it to do the calculations. I don't care what platform you use. Mathematica, you can write it in C, you can use it in MATLAB. For some reason, half of my aerospace engineers always try to program everything in Excel. Yeah. So I can already tell which lab you're from, or which lab you're not from, by how much work you're doing. That's awesome. So, interesting. So, yeah, I actually had a student trade like a 50,000 cell Excel sheet for this time. Okay, you can do it. It was right, I got more credit, but not the way I would have solved it. But the right answers are the right answers, so I don't argue. I've learned not to argue over the years, so it's going to give me the right answer. So, let's see here. Any questions so far? Pretty straightforward. Let me give some examples. Right now I'm going to switch over to the document camera because I brought some examples of some code See the light is on. We'll go ahead. There we go. Here we go. Let's see. Focus. Okay. There we go. Autofocus is working. So anyway, you can code this up, and as sort of a benchmark to your code on your homework, there's a little example problem where you just simulate the circular or elliptical orbits based on initial conditions. You can actually test your code or reuse the solutions online to tailor that code to your liking, how you want to do it. For the first part of your homework problem. But keep in mind it's only part of the problem. So here's the initial conditions I've got. An R of 42,000 kilometers from the Earth. So imagine the Earth is here. The Earth has a radius of 6,000 kilometers roughly, so it would take up about this much space. And I launched the satellite into what should be a circular orbit. So I set up the initial conditions of the geostationary Earth orbit that we learned about last class. 42,000 kilometers from the Earth. I just started it at 0, so it would be here along the x-axis. And you'll launch it this way. So the initial conditions are, well, it's circular, so there should be no R component of velocity. So you see that's 0. And I calculated, using that formula, remember the formula from yesterday, square root of GMP over R is your theta velocity component. That came out to 3.1 kilometers per second, 3,100 meters per second for a geostationary Earth orbit satellite, and I launched it with that tangential velocity. And then I just let that set of difference equation do the work. And it traced out a beautiful circular orbit. And sure enough, 23 hours and 56 minutes later, it got back to the exact same point, confirming that this is essentially a geosynchronous Earth orbit. Now, many of you, when you're going to do this exercise at home, will have something that looks like this. Here's your planet. You'll start your simulator. And you will get this. What is wrong? If you're using this technique to simulate the time progression of your orbit, what is likely wrong? Does anybody think of some culprits? Yes, that's usually exactly what it is. Remember, this is a discretized system of equations. It's not modeling the disturbances in between the samples. And so, the smaller your delta T, the more accurate it's going to be. At some point, if you make your delta T so big, it's not going to close up on itself. Now, there's a trade-off there, right? It takes a lot longer to really find delta T's. For this type of differential equation system, a delta T step of about 5 seconds will work pretty well for Earth orbits. You'll calculate, your computer will calculate the entire orbit in a matter of seconds, and it'll almost always close up pretty simply. Okay, let's try another example. What does this look like? What happens if I give a weird set of coordinates, a skewed set of coordinates? 30,000 kilometers as my starting point over here. 0 degrees, I'll always start it on X, because there's always rotational symmetry. I can always tilt it if I'm going to start it at a different angle. Without loss of generality, that's how you write that in physics. Without loss of generality, we can take any orbit equals to 0. And then look, I gave it a kind of a skewed set of initial velocities. But the R and the theta component have different values. 1 kilometer per second in the R direction, that would be here, and 2 kilometers per second in the theta direction, that would be in that direction. So you can see, not surprisingly, when I give any orbit non-zero d theta component, you're guaranteed to have something elliptical. And that's what we have in this case. It's a nice elliptical orbit. Here's another one. This is a highly eccentric orbit. Look what I did on this one. These are all actual homework problems, by the way, that I gave years ago for the class. So, I started off at an orbit of 6,000 kilometers. So pretend you're on the surface of the Earth. And let's also pretend that there's no air resistance, right? I launch at 8 kilometers per second d sub r and 1 kilometer per second d sub theta. So it's almost like shooting a projectile in the air. See, it goes up and it goes down. So there's a limit. In a limit of very small initial velocities. We almost get with the Newtonian mechanics of Earth-based